you've bought the same iPhone charging cable 4 times this year. Same spot, same bend, same failure. And you're probably thinking, I must be doing something wrong. But here's what nobody tells you about cable failure. It's not you, it's physics. And it's a design choice that could have been prevented from day one. In the next 15 minutes, you're going to understand exactly why your cables keep dying at that one spot near the connector. You'll see why some manufacturers intentionally design cables to fail. And you'll learn the simple engineering principle that separates a cable that lasts 3 months from one that survives 3 years. Because this isn't about being more careful with your stuff. It's about understanding a fundamental engineering concept that affects everything from your headphones to the cables powering entire data centers. Ready? Let's break it down. Picture this scenario. You're sitting on your couch, phone's at 15%, you plug in your charger and keep scrolling Instagram because, let's be honest, nobody just lets their phone charge anymore. You're holding it at this weird angle because the cable's not quite long enough to reach comfortably. And right there, right at that moment, you're creating a 90-degree bend exactly where the cable meets the lightning connector. You do this every single night, sometimes multiple times a day. Now here's what's really happening inside that cable while you're watching TikToks. Those copper wires, they're bending, unbending, bending again, over and over, hundreds of times, thousands of times. Think about it like a paper clip. Bend it once, no problem. Bend it twice, still fine. But bend that same paperclip back and forth 20 times in the exact same spot, and suddenly it snaps clean in half. Your charging cable is doing the exact same thing, except you're not bending it 20 times, you're bending it 20,000 times. And this matters because every single one of those bends is creating microscopic damage to the copper strands inside your cable. Little fractures, tiny breaks, metal fatigue happening at a level you can't even see. But here's where it gets interesting. This problem is completely solvable. Engineers figured out the solution decades ago. It's called strain relief, and some of the biggest tech companies in the world decided to remove it anyway. Wild, right? So what exactly is strain relief? It's basically a reinforced section of cable right where it connects to the plug, usually made of rubber or molded plastic, and its entire job is to gradually distribute the stress of bending across a longer distance instead of concentrating it all in one tiny spot. Think of it like this. Imagine you're trying to break a pencil. If you bend it sharply in the middle, it snaps instantly. But if you try to bend that same pencil into a gradual curve across its entire length, it's way harder to break. Strain relief does the same thing for cables. It forces the bend to happen gradually over several inches instead of sharply at one point. That single design feature can increase cable lifespan by 5 to 10 times. But here's what makes this even more frustrating. Early iPhone cables had strain relief built right in. Those ribbed, slightly thicker sections at both ends, that was strain relief. And those cables lasted years. Then Apple redesigned them, made them thinner, sleeker, more minimal, and they removed most of the strain relief to achieve that clean aesthetic. The cables started failing within months. Apple knew this would happen. They had the engineering data. But they made the choice anyway because a beautiful cable that breaks sells more replacement cables than a bulky cable that lasts forever. And that's exactly what happened to most people. You probably remember this if you had an iPhone between 2012 and 2016. Those cables were notorious for failing at the exact same spot. That weird fraying right where the white cable met the lightning connector. That wasn't random. That was predictable. Material fatigue happening exactly where the strain relief should have been. Now let's talk about what's actually happening inside your cable when you create that sharp bend. Your charging cable isn't just one wire. It's usually got 4 to 8 individual copper wires bundled together, plus shielding, plus an outer jacket. When you bend the cable sharply, the wires on the outside of that curve have to stretch. The wires on the inside have to compress. And neither copper nor the insulation around it likes to do either of those things repeatedly. There's this concept in engineering called bend radius. It's the minimum radius you can bend something before you start causing damage. For most cables, that's usually about 8 to 10 times the cable's diameter. So if your cable is about 3 millimeters thick, you shouldn't bend it tighter than about 25 millimeters of radius. That's roughly the diameter of a quarter. But look at how you actually use your cable. You're probably creating bends that are way tighter than that, maybe folding it completely back on itself. Creating bends with a radius of basically 0. Every time you do that, you're exceeding what the cable was designed to handle, and the damage accumulates. Copper is pretty flexible, sure, but it's not magic. It has limits. Here's where things get really interesting from an engineering perspective. The failure doesn't happen all at once. It happens strand by strand. Your charging cable probably has somewhere between 7 and 19 individual copper strands twisted together in each wire. When you create that sharp bend repeatedly, the outermost strands start developing micro cracks first. Eventually, those cracks propagate all the way through, and that strand breaks. But you don't notice yet because the other strands are still carrying current. Then the second strand breaks, then the third. Your cable still works, but it's getting weaker. Maybe you notice it's a bit finicky. Sometimes it charges, sometimes it doesn't. You have to hold it at just the right angle. That's not the connector being dirty. That's strands failing one by one until finally there aren't enough intact conductors left to carry current reliably. And by the time you notice the problem, the damage is already catastrophic. Those remaining strands are now carrying way more current than they're supposed to handle individually. They heat up, the insulation melts, and suddenly you've got exposed copper, short circuits, or complete failure. This is what I call the invisible degradation trap. The damage starts long before you notice any symptoms, and by the time symptoms appear, you're already in the failure cascade. Most people don't see this coming because they're judging cable health by whether it charges or not, but that's a lagging indicator. By the time it stops charging, it's been dying for weeks. But here's what nobody wants to admit. This isn't just about cheap cables versus expensive ones. This is about physics versus profit margins. Manufacturing a cable with proper strain relief costs, maybe 15 cents more per unit. That's it. 15 cents of molded rubber could extend the life of a $30 cable by years. But if you're Apple or Samsung or any major manufacturer, you're making millions of these cables. 15 cents times 10 million cables is $1.5 million in additional manufacturing cost. And here's the uncomfortable math. If your cables last 3 times longer, you sell 3 times fewer replacement cables. That's not just losing the manufacturing savings, that's losing the revenue from replacement sales. So you've got this perverse incentive where designing cables to fail faster actually increases profit. Not through planned obsolescence in some conspiracy theory sense, just through basic economic optimization. And once you see this, you can't unsee it. This same pattern shows up everywhere in consumer electronics. Laptop power bricks, headphone cables, USB cables, anywhere a cable connects to a device, you'll find this same engineering compromise. The question isn't whether manufacturers know how to make durable cables. They absolutely do. The question is whether they choose to. Let me tell you about 2 people. Both bought new iPhones on the same day. Jessica uses her phone constantly. She charges it every night on her nightstand. She holds her phone while it's charging because she likes to scroll before bed. The cable bends sharply right at the connector every single night, same position, same stress point. After about 4 months, her cable starts acting weird. Sometimes it charges, sometimes it doesn't. She wiggles it until it works. Another month goes by. The outer jacket starts fraying right where the cable meets the lightning connector. Little white threads poking out. She knows this pattern. She's been through it before. She buys a replacement cable from the Apple store for $30. She's careful with this one, tries to baby it. But the same thing happens because it's not about being careful. It's about physics. Jessica ends up buying 3 or 4 cables a year, spending over $100 annually just on charging cables. And she figures that's just part of owning a smartphone. Now compare that to Marcus. Marcus also uses his phone all the time, but Marcus read something once about cable management. When he charges his phone at night, he makes sure the cable has enough slack that there's no sharp bend at the connector. He also bought a third-party cable that had this chunky rubber boot at both ends. It looked kind of ugly compared to Apple's minimal design. But that rubber boot was forcing any bend to happen gradually over a longer distance. 5 years later, Marcus is still using the same cable. It cost him $12. He's replaced it exactly 0 times. Here's what's fascinating about this. Marcus and Jessica have basically identical usage patterns. Same phone, same charging frequency, same everything. The only difference is Marcus understood the engineering principle at play. He knew that sharp bends concentrate stress, he knew that gradual curves distribute it, and he chose products and habits that worked with physics instead of against it. Jessica thought cable failure was random bad luck. Marcus knew it was predictable material fatigue. Notice how different those experiences are? One person spends $100 a year replacing cables and thinks that's normal. The other person spends $12 once and forgets about it. That's the power of understanding this one engineering concept. Here's what most people don't realize about this whole situation. The cable failure pattern you're experiencing isn't a quality control problem. It's not defective manufacturing, it's the designed behavior of the system. When engineers design a cable, they know exactly how many bend cycles it can handle before failure. They have stress testing equipment that mechanically bends cables thousands of times to simulate years of use. They can predict failure within a pretty tight margin. So when your cable breaks at month 4, that's not unexpected. That's working as designed. The cable was engineered to survive roughly that many cycles under typical use conditions. And here's the thing that changes everything. Once you understand that, you realize this isn't about you being careless. These patterns aren't personal failures. They're predictable outcomes of engineering decisions made before you ever touch the product. The cables aren't breaking because you're rough with them. They're breaking because someone decided that a 4-month lifespan was acceptable in exchange for a thinner, more aesthetic design. And that decision affects everything. It affects how much money you spend on replacements. It affects how much electronic waste goes into landfills. It affects whether you trust products to last or assume everything's disposable. This is why strain relief matters. It's not just a technical feature. It's the physical manifestation of a design philosophy. It's whether durability was prioritized or sacrificed. Cables with good strain relief last years because they're designed to distribute stress properly. Cables without it last months because they concentrate stress in ways that cause predictable failure. It's the difference between engineering for longevity and engineering for replacement cycles. So here's what we've uncovered. Cable failure isn't random. It's material fatigue caused by repeated bending at stress concentration points. Strain relief solves this by gradually distributing that stress across a longer section of cable, and manufacturers often remove adequate strain relief to achieve thinner designs, knowing it reduces lifespan. Plus, there's the economic reality that shorter cable lifespans mean more replacement sales, which creates this weird incentive structure where durability actually works against profit. All of this connects to a deeper truth about consumer electronics. You're not just buying products. You're buying into design philosophies about whether things should last or whether disposability is built into the business model. The question isn't whether you can make your current cable last longer. With what you know now, you absolutely can. Just manage the bend radius. Give it slack. Don't create sharp angles at the connectors. But the bigger question is whether you'll recognize this same pattern when it shows up in other products. Because once you see how strain relief works, you start noticing it everywhere. Those chunky rubber boots on good quality cables, that's strain relief. Those rib sections on older electronics, strain relief. That slightly thicker, less aesthetic connector, that's engineering for durability instead of minimalism. And you can't unknow this now. You'll see cables differently. You'll notice which manufacturers prioritized looks over longevity. You'll recognize the engineering compromises in products before they fail. So next time you're about to buy a charging cable, ask yourself this question. Am I choosing the one that photographs well or the one that's engineered to actually survive? Because now you know what actually matters, and that changes everything.